So, good evening. Thanks for inviting me to give this talk, and sorry for the delay. The title of my presentation is Strengthening of Masonry with Textile Reinforced Mortar, and I will particularly deal with the strengthening of vaults. And as we all know, vaults are particularly brittle structures that could fail. We had a recent earthquake in Italy, and we had a lot of vaults that failed down, as you can also see in these slides. Especially the vaults which are very thin. They are maybe called in-folio vaults, and they have a really little thickness of about 5 centimeters, and they have a span of about 3 to 6 meters. And the idea to strengthen this structure is to put some textile reinforcement on the extrados of these vaults, and you could either place put the textile over the wall surface of the vault, or maybe put only some strips if the vault has a certain capacity and the reinforcement need not to be too strong. And the main idea is, since the vault usually fail by 4 hinges that have to form, and the hinge will form either at the intrados and then at the extrados of the vault, it is sufficient to put the textile either at the extrados or at the intrados of the vault to avoid the forming of hinges, because if you put at the extrados, you avoid the forming of hinge at the intrados and vice versa. And therefore, usually one simple strengthening is sufficient. And the strengthening I would like to talk about is the TRM, Textile Reinforced Mortar. We hear Professor Triantafillu speaking about these systems, and we hear also Dr. Gagegi speaking about this textile. Essentially, the system works in a easiest manner, because the textile is simply embedded into a mortar layer, and the mortar provides the bond with the substrate. So it's something which belongs more to the classical workmanship that you have in traditional civil engineering constructions. But as we have seen also today, there are many different systems comprising fibers with carbon, basalt, glass, PBO, and even steel. The kind of reinforcement I will talk about is a steel reinforcement. This is made by very thin cords, steel cords, made by ultra-high tensile strength steel with a strength of about 3,000 megapascal. And this textile is one directional only, and it is applied with a hydraulic lime-based mortar having a strength of about 20 megapascal. And the application process of this system is shown in these few slides. First of all, you have, if you want to apply over the extrados of the vault, first of all you have to polish the vault, remove the filling, then to arrive to the surface of the vault, to clean the vault in order to ensure that the reinforcement will be directly applied to the bricks, then to cut the strips of the reinforcement of the requested length, and put the reinforcement by putting a first primer to ensure a good application, to maybe, or simply to allow the surface to be humid, or to prepare also the surface to enhance the attachment of the matrix. Then put the first layer of matrix, place the reinforcement on the top of the matrix, take care of the connection at the end of the reinforcement, and then put the second layer of mortar. And if the vault has a double curvature, as in this case, we decided to place 2 different layers of this reinforcement over the 2 sides of the vault. And finally, we also build the backfill walls, and we put the filling on the vault to finish the intervention. Well, clearly, the behavior of this system is strongly dependent on the quality of the bond between the matrix and the substrate. And therefore, in order to investigate this bond, we make some in-situ testing in a rather simple way. We just apply the reinforcement over half of the vote, and then we leave the reinforcement without the matrix on the last part of it, after the crown. We take the reinforcement with two steel plates, and with these two steel plates were welded on a bar, and the bar was connected with an actuator, an hydraulic actuator. Then we pull the reinforcement from that point, as you can see in this slide. We put two strain gauge to evaluate the strain in the textile, and from the strain to evaluate the effective stress, to have a confirmation of the stress that was read directly by the actuator. And then we put two potentiometers in order to look at the relative displacement of the textile with respect to the substrate of the vote. And here you can see the setup that was very simple because it was made on site. And these were the tests that we carried out. The first two tests, as you can see, the two in red, they finished a little bit in advance because we were not expecting such a high level of load. Then we have to reorganize a little bit the supporting steel frame, and we were able to make the test up to the end, and the three tests in blue were made up to the end, up to the complete detachment of the textile from the vote. And you can see here some images of the progressing of the debonding process that involved a complete losing of the exterior part of the matrix, of the mortar matrix, and the slippage of the textile over the substrate. And this is more or less our interpretation of this result. You have a first uncracked behavior in which the full bond is provided. Then you have the progressive debonding taking place within the matrix, within the mortar matrix. And so we have this second cohesive contribution. And then you have a third important frictional contribution, which arises from the length of the textile, which is applied to the reinforced to the vote, and also arises from the curvature, so that the textile, even if it's detached from the substrate, will provide some bond due to the friction that arises. And to better understand the increase in terms of strength and displacement capacity, we also make a test in the laboratory, and we make a test on a vote sample spanning about a little bit less than 3 meters and thickness 5 centimeters and a half, and width of about 50 centimeters. So the specimen was provided also with backfill walls, as you can see here, and with filling, as you can see here. And we take care of preparing the surface of the vote with this pattern, and also to buy sand, gravel with two different colors in order to have a pattern and to be able to use digital image correlation to capture the wall displacement and strain field of the specimen. Here you can see the votes. We tested two votes. One was reinforced and the second was reinforced with the steel reinforcement that you have seen before. And we just place one sheet of reinforcement having 30 centimeter width with respect to the 50 centimeter of the vote. The displacement measure were not only the digital image correlation, but we also use some potentiometers, two vertical potentiometers on the 2 points, the Voussoir 10 and 17, that was expected to have the maximum vertical displacement. And we also put several strain gauge over the textile in order to record the effective strain on the textile. And here you see the attention that we pay to use the speckle pattern on the surface of the specimen, to use digital image correlation for detecting the field. And here you can see, hope that it will work, one of the tests, but it's not working, unfortunately. Maybe the film is not working, but it's not. Okay, this is one of the tests. We made some cyclic tests, as you can see here. Up to the complete failure, we have to move away that was the test on the reinforced vault, while this was the test on the unreinforced vault, but it's not maybe working. Okay, we don't mind. Here you can see the particular of the failure that takes place. In the unreinforced vault, the failure takes place with the classical hinge, as you can see here, while in the reinforced spacement we again have some hinge, but with compressive failure in the hinge area, and we have also some sliding in the area where the reinforcement, where the load was applied. The load was applied at 1/3 of the overall span. Here you can see the displacement at a different step of the test, and the reconstruction of strain and displacement field from the digital image correlation. This probably is the more clear result, which display the load to displacement, to vertical displacement component of the loaded point on the right, and to the upward displacement of the other voussoir that was recorded during the test. As you can see here, the behavior of the unreinforced vault is represented in blue. You see that we arrived to load capacity of almost 6 kilonewton and an overall displacement capacity of about 40 millimeter at the ultimate displacement before failure. With the reinforcement, the increase in strength was significant. We arrived to about 15.9 kilonewton as ultimate load, and also the increase in displacement capacity was significant, since we arrived to an ultimate displacement of about 88 millimeters in wall. And so that's our experience, and I would like to acknowledge my co-authors, which are Stefano De Santis and our group of the laboratory with Mario, Lorena, and Roberto, which are the technicians of the laboratory. Thank you very much for your attention.
So we can take a couple of questions. Any question for Gianmarco?
I have maybe one.
Please.
How is the situation in Italy about designing such kind of textile reinforced for structural applications, since there is in the field? So how engineers go to design such kind of reinforcement?
No, this is a very important question. Thank you for your question, because at present time these systems are used in practice without a regulation. There is now a guideline for the qualification of this system, of TRM system, which is currently submitted to the Consiglio Superiore dei Lavori Pubblici, and is supposed to be approved in the next few months. But this is only the guideline for qualification. That means that tell you which are the tests that you have to perform in order to allow your product to be used for structural reinforcement. But on the field of how to design the reinforcement, there is really no guideline yet. Some engineers, they use the guideline for FRP. For instance, in Italy we have the CNR DT 200, which is a well-known document, which is currently used also for TRM systems, but it could be a good substitute to in the absence of effective guideline, but it doesn't work all the time, and moreover you don't know effectively which are the material parameters to take to make the design, because the material parameters are not clearly defined at present time. So it is really a challenging problem. And I would say also that the RILEM committee that I'm chairing, the RILEM TC 250, is currently working together with the ACI 549, which is the current guideline available on what they call FRCM systems, and we are trying to draw some jointed guideline between ReLEM and ACI in order to have some support for practical design of this system.
Thank you. Any other questions? Then I'll have one quick question, maybe. You mentioned, I really like this steel TRM material, and I think they're really interesting and they can have some very good applications. You mentioned that you put strain gauges on the fibers. Yes. Were you able to strain gauge the fibers? And how much strain do you actually, how much do you use of this material? Because it looks like it's a very strong material, stronger than maybe what you need to strengthen these type of structures. How much are you using of the material itself?
No, well, in application to masonry structures, usually you don't need, it is sufficient a textile with few cords in order to allow sufficient spacing and for the mortar protrusion and to ensure a good bond with the mortar. The first advantage of using steel is the fact that the steel cord is as a interlocking within the mortar. So you don't have some mechanism of sliding of the textile inside the mortar, which takes place, for instance, when you use carbon or you use basalt textile. While with steel textile, the cord are really interlocked with the mortar. So the failure that takes place usually takes place with cohesive cracking within the matrix under the textile. So if the textile is made by too many steel cords, you don't allow the mortar to penetrate among the textile, among the cords, and you will have a lower bond capacity. And so usually you have from 4 to 6 to 8 cord per inch is sufficient for ensuring a good performance of the application of this system over masonry structure. Especially if you use low matrix properties. If you use higher matrix properties, for instance, you use a cement base or polymeric modified mortar with microfibers inside, you will have a stronger mortar and you can have a higher density textile. But if you use a lower class of mortar, for instance, a lime-based mortar as a matrix, you really allow, it is sufficient to have 4 to 6 cord per inch for the textile.
Thank you. Thank you,
Maurizio.